on. All right. Welcome back to Real Analysis. If you recall from last time, the last couple lectures, we were talking about sequences. And today I want to begin an associated topic, and that's the topic of series. Okay? But just to dust off the cobwebs a little bit, let me just remind you what we did last time. So last time the last couple of lectures, we defined what it means for a sequence to converge, and we had this notion that basically said that a sequence converges if, no matter what distance you name from the proposed limit, there's a point in the sequence beyond which all the terms are close to the limit. Okay? We had an associated notion of a sequence being Cauchy, which basically said for any target distance that you name, there's a point in the sequence beyond which all the terms are within that distance of each other. Okay? And we showed that convergent sequences are Cauchy, and we defined a concept of a complete space, which is basically spaces in which Cauchy sequences converge. Okay? And we showed, in fact, that R is complete. So the notion of being Cauchy and being convergent is exactly the same. And this is great news for us. Okay? It's great news because if we want to show that something converges in R, all we have to do is show that the sequence is Cauchy. That is, the terms eventually get close to each other. Okay? There was a question last time which, so something that we did last time, which I didn't mention on this slide, is we also hinted at or alluded to this amazing fact that if you have a space that's not complete, you can complete it. Okay? There is a completion, which is basically defined to be the set of all Cauchy sequences under some equivalence relation, right? And if you take a look at that and you can put a metric on it in a nice way, your homework asked you to explore that, you get a space that is in fact complete. And I mentioned that this was an alternate construction of the real numbers from the alternate construction of real numbers that's different from the Dedekind cut construction. And somebody asked the question, well, how do you do that if it looks like you're making definitions in terms of limits of distances, right? And I just wanted to address that a little more this time because I thought about it. And there's really not a problem because if you just define the concept of you just avoid referencing limits, you can still do everything, right? All you're doing is constructing the space, and it's only later that you actually define a metric on the space, right? So you define the set of all Cauchy sequences. You can talk about what it means for two Cauchy sequences to be equivalent, and you can just avoid referencing taking the distance between 2 points. What do? You're just talking about the difference of two rational numbers, right? You can talk about that. You can say what it means for that to get small, close to 0. So there's really not a problem in constructing the reals from rationals that way. Okay, so what do we want to do today? We want to talk about series, which is basically an example of a sequence. So let's make some definitions here. So just to get the ball rolling, the motivation is to try to understand sums of the following form. So let me ask you a question. Tell me what this means. What does this mean? Here's a question. So I put up some expression like this. 1 plus a quarter plus a ninth plus a 16th plus ... Of course, if I didn't have the ... you would know what this means, right? We talked about addition of fractions, right? But as soon as I put in a ... we are once again wrestling with the infinite, right? There's some sum that is infinite, right? Okay? What does it mean? And what does it mean if I tell you that this is actually pi squared over 6? What does it mean? There's a question, okay? And just to show you that it's not, the answer is not necessarily obvious, tell me what this means. What if I gave you a sequence, a series, this is called a series, like this. 1 minus 1 plus 1 minus 1 plus ... Could you make sense of this? Does this mean anything? I mean, for instance, you can't stop me from perhaps grouping the terms like this, and then perhaps you might think the answer is 0. 0 plus 0 plus 0. And surely nobody can argue that a sum of a bunch of zeros, even if there are infinitely many of them, it should be 0, yeah? But, maybe one of you decides to group them a slightly different way. How about 1 plus minus 1 plus 1 plus minus 1 plus 1, ... So we have 1 plus a bunch of zeros, and surely nobody could argue that this ought to be 1. Yeah? Or maybe you want to argue with Euler, who said that this thing should be a half. What? Okay, so we have to actually make this, we have to make this concept meaningful somehow, okay? Can't just throw around a bunch of infinite sums and expect everybody to get the same answer, okay? Okay, well, so there are some things that some things we have learned, right? We've learned a few facts, I think, probably from your grade school days. You know how to add things that look like this. ... yes? Some of you even know a name for this kind of series. It's called a geometric series. Okay, yeah, and maybe you know how to add these up. You, for some interesting reason, you take the reciprocal of 1 minus the successive ratios. Yes? Okay. And the reason you know this is because it's a special case of something like this. 1 plus x squared plus x cubed ... equals 1 over 1 minus x. Right? Okay, but once again, you have to ask yourself, why? Why is this true? And, well, okay, you might, for instance, verify it this way by multiplying out these polynomials and getting 1, right? And, well, does this make any sense? Well, as a formal object, yeah, maybe it does, right? I mean, like, here I do 1 times all of these and minus x times all of these, and oh, interesting. We get some grouping and some cancellation that looks something like this, but again, we're still kind of, we're worried a little bit, right? What does it mean? Okay, well, you could then, of course, if you're not too careful, begin to add some things like this, right? And then you get 1 over 1 minus 2, which is otherwise known as minus 1. Yeah? If you're not too careful, this is some of the ridiculousness that you might get. Maybe even as interesting, alternating sum of the 2 to the whatever is 1 over 1 minus a half, otherwise known as a third. Yeah? You okay with that? How many people are okay with that? You're not okay with that? What about plugging in minus 1 here? Well, okay, yeah. So, in fact, this is, in fact, a half. And Euler would have been fine with this. But he was wrestling with the same thing we're wrestling with, is trying to make sense of, could this mean anything, right? Could this mean anything? Is this meaningful? We wouldn't accept such nonsense today, right? Yes, Harris. Yeah. Oh, thank you. Thank you. -2. Thanks. Yes. Yep. Yeah. So I mean, okay. So I mean, Euler was trying to grapple with whether this could even be something meaningful, right? Could it? I mean, even if it looks like nonsense, maybe if you just play with things the right way, you get things would work. I mean, who knows, right? So, okay, so we have to actually make sense of this in some way, and let me show you how we do that. So, here's how we'll define a series. A series is basically a special kind of sequence. So suppose I'm given a sequence of terms, a sub n. Then what I'm going to do is I'm going to define. Okay, so maybe I first have to define what I mean by a summation symbol. I'm sure most of you have seen a summation symbol. But if I say I'm adding up a bunch of terms, a sub n, going from p to q, this symbol just says go from the pth term to the qth term. Okay? That's a summation symbol. Well, then what I'm going to do is I'm going to let S sub n be the sum of k going from 1 to n of a sub k. Notice now the index is k, and this says add up what? The first n terms. Okay? This is called the nth partial sum. Okay? So in this example here, the first partial sum, if this is the first term, the first partial sum is, this is S1, this is S2, this is S3, this is S4, yes? Those are the sums. Okay? Okay. Now, would you agree that these partial sums form a sequence? It is a sequence. So the series of the ANs, which we are adding up, form a sequence, associated sequence of partial sums. And this sequence is, well, it's a sequence. It may or may not converge, right? You could ask whether it converges. It may or may not converge. So, so let me just make some notation here. So this sequence is sometimes written so you write basically as a sum, the summation symbol, n equals 1, and we put an infinity up here to just remind ourselves we're trying to do something that looks like an infinite sum, but we're thinking of this notation as representing the sequence. Okay? And this is called an infinite series. Hold that comment. So now this may or may not converge. May not converge. But if it does, let's say to S, some number S, then we'll write the following. Sum from n goes from 1 to infinity of a sub n equals S. This is just saying the same thing as sequence of partial sums converges to S. So what I want you to notice, this is the important point, is I'm making a definition of what this symbol means. If I say n goes from 1 to infinity, whatever this means, what I mean is this is the limit of n goes to infinity of the SNs, right? Or, if I like, the limit as n goes to infinity of the partial sums. K goes from 1 to n, and I'm summing the a sub k's. This is really what that notation means. Okay? Jenny. Good. A series is a sequence. And it's the sequence of partial sums. But we notate the series by writing, we'll write this, and whenever you see this symbol, you should think this is a sequence of partial sums. A sequence is not a series. So I think I see what you're getting at. So sure, if you give me some sequence, I suppose you could create a set of a sub n's for which that sequence is the partial sums of that sequence. You certainly could do that. But when we say series, we're thinking that there are some a sub n's from which we are creating the partial sums. Okay. Yeah. So informally you can think of series as sums of a bunch of terms, and formally we're saying no. What we mean is the partial sums here actually as a sequence. Okay. Okay. Great. So there are some natural questions. I've just defined a series as a sequence. So you probably want to know, when does a sequence converge? Okay. Okay. So when does a series, so we say a series converges if the associated sequence does converge. Okay. Okay. Well, there's an easy answer to that. We'll say a series converges if its sequence, the associated sequence of partial sums does. When the sequence of partial sums do. But that trades one problem for another problem. When does the sequence of partial sums converge? When is that? There's the question. Okay. Okay, so, well, let me have you recall an example we saw last time. We actually studied a series last time. I didn't call it that. But you might ask yourself, if a sub n is 1 over n, what about this series? 1 plus 1 half plus 1 third plus 1 quarter plus dot, dot, dot. This is a series. Does this series converge? And when I say that, what do I mean? I mean, does the sequence of partial sums converge? Okay. Now, this series has a special name. It's called the harmonic series. Okay. When does this converge? How did we answer that question last time? Now, I didn't write it this way either last time. Last time, I actually just wrote out the partial sums. I said Sn equals sum of 1 through, here the partial sums are the sum of 1 through the nth term. Yeah, I think that's the way I wrote it last time. How did we decide if it converged? We used Good. We used a Cauchy criterion. We just checked if it was Cauchy, right? So that's actually exactly what we're going to do to determine, in general, what happens. We'll just check if the sequence is Cauchy. So we checked if it's Cauchy. Does this converge? Is Sn Cauchy? Now, recall again, what did it mean to check that Sn was Cauchy? We wanted to look at the difference of partial sums, Sm minus Sn. Right? But what is the difference of partial sums when you're adding the first m terms and subtracting the first n terms? It's just all the terms in between. Oh, so for a series, checking the Cauchy criterion amounts to just checking a bunch of tails of things. So this, in this case, was something like if m is bigger than n, then this is going to be an plus 1 plus dot, dot, dot through am. Or actually, maybe it starts at an plus 1 through am. Right? It's all the terms in between. Okay. And we saw that in this case, at least, we could show. So last time, we showed, in fact, that if you take s sub 2n minus s sub n, that you could always get this thing to be bigger than a half. And therefore, this thing is not Cauchy, especially if you took epsilon less than a half. Okay? There's no point in the sequence beyond which all the terms are close, because you could always find a number and a sequence element and something twice as far out whose difference is bigger than a half. So this sequence is not Cauchy and does not converge. And this is the general criterion. So this is what we call the Cauchy criterion for series. The other thing is, of course, just the Cauchy criterion for sequences. But for series, what we have is the following. A series, A sub n, converges if and only if. And by the way, if I stop writing the indices here, I mean n from 1 to infinity. Okay? This series converges if and only if, help me, for every epsilon bigger than 0, there exists an n such that, help, little m bigger than big N implies, help, the distance which ends up being what? A bunch of things. Yeah. Let's take the sum from k goes from n to m of a sub k is less than epsilon. Okay. And in fact, it exactly comes from that intuition. What you see here really is this is a bunch of tails of the series. So what I'm really looking at is, in a series like this, is past some point, are any possible sums you take past some point always going to be less than epsilon? That's the question. Okay? So, are you happy with that? Yes? Okay. So, let's just see what this means. There's a lot of things we can tell from this fact, and this just follows from that intuition. So, I've basically done the proof. So, there's an immediate corollary we'll get. What if I let m equal n? What corollary, what can I say? If I let m equal n, then if a series converges, this implies that what? If I choose m and n to be the same, the terms have to go to 0. Because the terms for any epsilon, there's some point in the sequence beyond which all the terms are smaller than epsilon. So this means that the limit of the a sub n's is 0. So the terms go to 0. This is sometimes called the term test for convergence. Okay? Now, the converse is not true, right? And it's not implied by this theorem either, right? Because this is saying if it converges, this has to be true for all possible m and n, bigger than big N, right? But why is the converse false? Can you see an example? Harmonic series. But we see the very familiar term test as a way of, you know that if the terms don't go to 0, the series can't converge. Drew first and then Jenny. Yes, well, we're all in here. We're always talking about real numbers because we're talking about adding elements of this space. Oh, yes, that's right. Yeah, we're talking about real numbers. Yes, not subsets of real numbers. Okay, so yeah, we're talking about real numbers, not subsets of real numbers. Jenny. Oh, same question as well. Yes, we're talking about real numbers only. Very good. Great. Immediate consequence of the Cauchy criterion. You just have me thinking now, like if we're in the rationals, what is there anything you can say? Is this theorem false? Obviously. Yeah, I mean, certainly. If you take that series, the very first one, which converges to pi squared over 6, which is not rational, another theorem probably you have to prove, but that would be an example where this series does not converge in the rationals. But yet the terms are all going, all the tails are getting small, right? Okay. Excellent question. Okay. Let's see. What else can we say? Oh, gosh, there's a lot of other immediate consequences. Here's one. Theorem. This is a theorem about non-negative series, which means all the terms are non-negative. If a sub n is bigger than 0, then, well, I claim convergence of a sub n converges if and only if the partial sums are bounded. Can anybody see why? Anybody see why? Okay, excellent. So if a sub n is bigger than 0, all the terms are bigger than 0, would you agree the partial sums are increasing monotonically? And we know from the theorem last time that monotonic bounded sequences must converge. Okay. Proof. If a n is bigger than 0, the partial sums are monotone, increasing. So if they're also bounded, but bounded monotone sequences converge. Very simple corollary. Again, consequence of the Cauchy criterion for series. Okay. All right. Hey, that's a lot of mileage for just a simple consequence of the Cauchy criterion. Here's another one. Oh, this one's great. What's another theorem that you've learned from calculus to help you decide whether a series converges? Well, let's see. You give me some series, and maybe I don't know anything about it, but maybe I know something about another series. What do you often try to do when you have a series you know something about and a series you don't? Compare them in some way. Bound one by another. Okay. Why is that true? So this is a comparison test. Here we go. The first thing comparison test is let's compare a series A with a series Cn, A sub n, and C sub n. Suppose A sub n and absolute value are bounded by the C sub n's, and we actually only care if n is large enough. In other words, whether a series converges or not, would you agree, doesn't really depend on the first few terms? Doesn't depend, right? Because it'll just shift everything. So if you know that an is bounded by Cn for n large enough, and the series C sub n converges, then what can we conclude? An converges. Okay. Statement B is not is similar. Suppose an is bigger than d sub n, and they're both bigger than 0. And the thing I want to point out here is you have to be careful when you apply this theorem. Notice I'm requiring them both series here to be non-negative. Okay. So if an's bigger than dn, is there anything I can say about an if I know something about dn? Good. And suppose this is true for n large enough. So a lot of you are saying, okay, if the sum of the dn series diverges, then an diverges. This is one of the most useful tests for convergence of series. And in fact, it follows from our criterion. Let's see why. Proof. Let's do A, proof of part A. Well, since Cn converges, we have a Cauchy criterion, right? Cauchy criterion says, since Cn converges, for every epsilon there's an n, such that when the terms are big enough, the tails are small, less than epsilon, tails of the Cn, right? Oh, okay. Which means for every epsilon bigger than 0, now, of course, the epsilon that we're going to be dealing with is, what are we trying to show? We're trying to show that the an converges, yeah? So I'm going to use the Cauchy criterion for the a sub n. And I need to find, my goal is to find a what? For every epsilon, find an n that works for that. So maybe I should start this proof off here. Given epsilon bigger than 0, we'll use a Cauchy criterion to show the an converges. Okay, so actually this is not a sentence, is it? I should say fix epsilon bigger than 0. Period. Since the Cn converges, for this epsilon, there exists an n such that m and n bigger than big N implies some sum of the ck's is less than epsilon for k from m to n. True? Now what I want to do is show the same criterion for the a's. And I need to find a big N that works for this epsilon and with ak here. But what n should work? Excuse me. Sorry for coughing into the video. Sorry. Just got a cold. Okay. Yeah, so which one works? Well, certainly this n works, and as long as this condition also holds too, right? So we're in good shape. So Um, let's, okay, so there exist an n such that mn bigger than big N is less than this. I guess because of the n large enough condition, this thing holds for some, let's call this n1. This condition holds for some n bigger than n2. So maybe I'll say n bigger than n2. So I'll let n be what? Yeah, how about the maximum of those two places in the sequence, those two indices? Yay. And then for this n, for n, little n and n, bigger than big N, what do we see? Well, we see the sum of the a sub k's. Help? Why? Okay, so I need to relate this absolute value to 1 with the absolute value around the AKs before in the sum outside, which I can do by the triangle inequality. Hurrah, I'm not writing the indices here, but you know what they are. Ah, triangle inequality right here. And then this is nicely bounded by the CNs. And this, I know, is small. If this absolute value is small, well then this thing is less than epsilon for sure, as desired. Okay? Question? The question was about the indices, when to use k or n. It doesn't really matter, except that I've chosen to use k in this condition because k is the index because I'm going from m to n, and I've used those letters here. But of course, you can use any letter. But I've just notationally done that to remind you that I don't want the same index here name as I'd used here. Oh, this should be a K. Thank you. That's your question, isn't it? And I didn't write out all the indices here, but you know what they go from M to N. Okay. Excellent question. Other questions? What have we just done? We've proven the comparison test using the Cauchy criterion, right? I've just shown all the major theorems of most of the major theorems about series are really convergence tests for series boiled down to nice proofs with the Cauchy criterion. Why is this thing its tail small? Because they're bounded by these things, and those things have small tails. Okay, what about B? Part B. Well, let's see. Jeremiah's thinking part B looks a lot like part A, but somehow flipped around, yes? Well, let's see. So I know something about the DNs, and I want to conclude something about the ANs. Wouldn't you agree that I could just use part A to do part B? Why? I'll use part A, and noting that if the contrapositive of part A is if AN converges, so does DN, right? So does the sum of the DNs. That's the same statement, isn't it? To say DN diverges implies AN diverges is the same as saying AN converges implies DN converges. But now, how do I show that if AN converges, DN converges? Well, DN is smaller than AN, right? In absolute value. And I needed the non-negativity here. And obviously, I need non-negativity in this statement, because if I didn't have non-negativity, is it possible that dn diverges but an converges? Yeah, especially if the dn's are really negative and you're adding a bunch of negative things and they're going off to minus infinity, right? Okay, very good. Use a to show. And that's the contrapositive. Okay, excellent. Comparison test. All right. So now that we have the comparison test, a good thing to ask yourself is, what should we start comparing things to? What to compare to? Well, the first basic sequence to compare to is the geometric series, yes. Okay. Geometric series. So here's a theorem. This geometric series appears in the theorem. If the absolute value of x is less than 1, then, in fact, this sum, n goes from 1 to infinity, is 1 over 1 minus x. There. This is the sum formula that we've learned since maybe grade school. Actually, I don't know when you learned this. High school? Is it high school? Okay. Analysis. Okay, what can I say if x is bigger than 1 and equal to 1? Yes, the series diverges. Again, I'm stopping writing this whenever it's the indices when it's obvious. But this is something we also want to know. So it only converges if and only if the absolute value of the ratio that appears in the geometric series is, in fact, less than 1. Okay, how are we going to show this? How are we going to show this? Now, of course, it wouldn't, we're going to try to use comparison to compare lots of things to the geometric series. How are we going to show the geometric series converges when x is less than 1? Help? One plus x squared plus x. Well, to show something converges directly, you should go back to the partial sums. What are the partial sums? Here we go. I'm going to assume for the minute x is not 1. Then I'm going to let Sn be 1 plus x plus ... through x sub n. Okay? Now, this is a finite sum. So you really can't stop me from multiplying this by x minus 1, or 1 minus x, and seeing that you actually just get 1 minus x to the n when you do it. So Sn actually is clearly, you just factor, if you like, 1 minus x to the n plus 1, and you can factor out a 1 minus x. Okay, so this is just polynomial arithmetic. Usual polynomial arithmetic. You can see why that's true. Help. Now what? This is a partial sums. Yeah, take the limit. Very good. So the limit of the SNs is, well, it's the limit of 1 over 1 minus x, which has no dependence on n, times, so this is the limit of a product, is a product of the limits, times the limit of 1 minus x to the n plus 1 as n goes to infinity. Yes? Help? Well, this is what? Here. Let's just assume from the beginning x is strictly less than 1. Help. What can we say here? Yeah, it goes to 0. Sorry, 1 minus 0. Yeah, so this thing goes to 1 minus 0, so we get 1 over 1 minus x. Done. Notice that this is true if x is less than 1. That's where we've used it. Okay? So if x is less than 1, we have this as the limit. Now, if x equals 1 or minus 1, what can we say? Or, in fact, how about just take care of the whole case? X bigger than or equal to 1. Why do we know this thing diverges? A little easier. Terms don't go to 0. Right? Terms do not go to 0. So the sequence diverges. The series, sum of the xn, diverges. Excellent. Excellent. Any questions about this? In one fell swoop, we've actually just eliminated many of the major theorems about series, right? And we care a lot about series because, well, let's see, there's lots of examples from calculus, right? If you're doing limits of Riemann sums, that's the sum of a bunch of little areas of blocks, right? If you're constructing wave functions, waveforms from a bunch of sines and cosines, you're adding up infinitely many of them, you have to worry if the sums at any given point actually converge. That's a series. Okay, great. So what else? Let's take a couple-minute break, and after the break, I want to show you a few more series that we can say something about. We have to be a little more clever, though. Okay, let's take a couple minutes. Okay, let's resume. So earlier we showed that the harmonic series, which is the sum of the reciprocals, diverges, right? Diverges. It does not converge. So Leon must be wondering, here's a question. What can we say about the sum of 1 over n to a power? Does it converge or diverge? And if so, for which p? You know, if p equals 1, it diverges. What if p is bigger than 1? Well, if p is 2, you get pi squared over 6, right? What about p equals a half? What about p equals minus 2? Okay, question. There's a question, okay? Do we have any tool? So first of all, any conjectures here? Sum of 1 over n to the p. When would you suspect it converges? P bigger than 1? What if p is 1.01? How do you know? Well, it's bigger than 1. But what would you compare it to? How would you show that it converges? Maybe by some comparison, right? Maybe, right? But it's a little problematic because it's unclear how you would show, how you would even work with that. 1 over n to the 1.01. Okay, so let me show you a theorem that might help us in a very cool way. So this theorem may look completely unrelated, but it's very cute. This is a theorem of Cauchy. Most theorems in analysis, not most, lots of theorems in analysis are due to Cauchy, who really wrestled with many of these things. Okay, here we go. Suppose I have a bunch of terms, A1 bigger than A2, bigger than A3, dot, dot, dot. They're monotone decreasing terms, and they're all bigger than or equal to 0. Okay, so it's monotone decreasing. I claim the following. It's a very interesting criterion. It says, if I want to determine convergence of the ANs, it's equivalent to just looking at some of the terms. I don't have to look at all of them. I'm going to look at every power of 2th term and multiply that by that power of 2. Let's look at 2 to the k times a sub 2 to the k. And I claim that these converge or diverge together. Okay, so this is an interesting fact, maybe not so familiar. How many people have seen this theorem before? Yeah, okay. If you've done the reading, you've seen the theorem. So let's see. What is this series, right? This series is basically A1 plus 2A2 plus 4A4 plus 8A8. Yes? Okay, so we have some sense of what it is. So I'm just going to give you the proof idea. We are going to do this by comparison. And what's cool is I'm just going to compare these terms, these sequences to each other. Okay? So let me convince you that, at least in one direction, there's a good comparison. Let's let S sub n be the sum of the first n terms. Let's let T sub k be the sum of the first k terms of the powers of 2 sequence. So this is the partial sums. Okay, happy with that? It's just what. So let me in fact make this a little more explicit, and then you'll begin to see what comparison I'm about to do. Check this out. Sn has as its partial sums, would you agree it's the sum of A1 plus the sum of A2 and A3 plus the sum of A4 plus ... A7, etc. Keep going. Here this is the sum of the first n terms, but if you don't mind, I'm just going to group together A1, the second 2 things, the next 4 things, etc. Okay. Now, you see why I'm going to do this? Because TK actually is this sum. It's A1 plus, what's 2A2? Well, that's just A2 plus A2. Yes? And what's 4A4? That's just A4 plus itself 4 times. Yes? So Julian's looking at this and smiling because he sees a good comparison. What's a good comparison here? Well, just compare this grouping with this grouping, right? And the only thing that changes here is this A3 turns into an A2. Yes? And the A5 through 7 turns into lots of A4s. Yes? So which direction am I going to make a comparison here? Let's see. Going here to here, did I increase or decrease? I increased. Okay. So here, I'm going to make the comparison that I'll imagine this converging, and then if this converges, this one will. Would you agree? As long as I pick n and k appropriately. So that's the idea. Notice if n is less than 2k, then Sn is less than tk. That's really what we've just done. As long as the top sequence ends before the bottom sequence goes out to that point, we're in good shape. Then everything else you have is extra. Okay? That's the idea. Okay. Now this will give you convergence of this implies a convergence of that by comparison. Use comparison. That's the idea. What about the other direction? Well, check this out. In the other direction, look at this. Let me show you what 2SN looks like. 2SN, would you agree, is 2A1 plus 2A2 plus 2A3 plus A4, yes? Plus 2A5 plus A7. Oops, sorry. Not what I wanted. 2A3, A4. Yeah, A5 through A8, I think, is what I want. Plus dot, dot, dot. Would you agree with that? I've broken up the first A1 and A2. I left it themselves, and these I'm going to get a group. But now, check this out. What is TK? Now, I want a comparison in the other direction, right? So really, here's what I'm doing. I'm going to match this up with A1. And this one I'm going to match up with A2 plus A2. And then this one I'm going to match up with 4A4. This one I'm going to match up with 8A8. Okay? And now, once again, I have a comparison, but now in which direction? I can make this bigger than this. That's the direction I want, right? Isn't A1 smaller than 2A1? Aren't these smaller than this? And this smaller than this because A4 is smaller than A3? And this smaller than this because these things are smaller than A5 through A7. And once again, and you go out to the last term, whatever AN is, right? And this goes out to TK. But the point is, if, yeah, and this isn't dot, 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 but this goes out to TK and AN. Nice. Okay. N is bigger than 2K. If N is bigger than 2K, then what we have a good comparison. We have TK is less than 2SN. And then we'll use comparison here. And if the SN converges, so does 2SN. Okay? So that's the idea. Very nice, beautiful idea. All right, so great. This is it might just be a curious theorem, except that it's actually extremely useful now to show what happens to sum of reciprocal powers. Yes? Yeah, well, remember, we are talking about infinite series in the theorem, but infinite series are really sequences of partial sums. Those are finite. That's right. And so we're back to working with the finite, which is what we want, but we now have to just figure out what that limit is. Okay, so here's the application. Let's come back to 1 over n to the p. Check this out. I claim this sum, 1 over n to the p, converges just as you claimed if p is bigger than 1. And it diverges if p is less than or equal to 1. Let's prove it. Can you see what we're going to do? This is so cool. This is just so cool. Okay, let's first dispose of a case where it's clear it doesn't converge. If I take p less than 0, then this just becomes powers of, it's 1 over n to the minus 2, right? That's n squared, sum of n squared. Clearly doesn't converge. Terms don't go to 0, yes? So as long as p is less than or equal to 0, the terms don't go to 0. They don't go to 0, so it diverges. So the series diverges. Get that out of the way very quickly. So if p is bigger than 0, then, okay, it might be positive somehow here. Check this out. We're going to use the previous theorem. We'll take a look at the series where you pick out the 2 to the kth term. So there's 2 to the k. And what's the 2 to the kth term of 1 over n to the p? That's 1 over 2 to the what? kp. That's what I'm looking at now by the previous theorem. But what is that? This is 2 to the 1 minus pk. It's the sum of 2 to the 1 minus pk. What kind of series is that? Where this is a sum over k. It's geometric. Beautiful. And we know the geometric series converges when the ratio is strictly less than 1, 2 to the 1 over p, right? Which converges exactly when, if and only if, 2 to the 1 minus p is strictly less than 1. But when is 2 to the 1 minus p strictly less than 1? So this is true if and only if 1 minus p is less than 0. And so that's, in fact, gives us the condition p bigger than 1 is when it converges. So this is only true. This is true if and only if p is bigger than 1. And it diverges otherwise. Okay, so we've just answered our question, sum of the reciprocal powers. Very, very nifty. Took a little work. But now, actually, we have a very good set of things to compare to. We no longer have to just rely on geometric series or harmonic series. We have all those series, the reciprocal powers we can use now as things we know convergence or divergence of. Okay. All right, great. Now let's finish with a cool application. Here's a series that arises in many contexts. 1 over n factorial, Taylor series being a prime example. Anybody know what the sum of the reciprocals of the factorials are? Sum 2? This sum actually goes from 0 to infinity. 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial. Anybody know what it converges to? First of all, does it converge? That's a question. How many people say it converges? Yes, you're right, it converges. Good. Okay. And it converges to a limit we call E. To something we call E. That's how we can define E this way. Okay? But let's just convince ourselves it converges to something. Well, why does it converge to something? Help? Use any of the theorems we've talked about before. Partial sums are, okay, yeah, the terms go to 0 doesn't necessarily mean it converges, right? If the terms don't go to 0, we know it diverges, but if it goes to 0, well, it may or may not converge. What else do you know? Are the terms non-negative? Yes, good. So the terms are non-negative, so this sequence is increasing. So if we could show it's bounded, we're in good shape. The partial sums are bounded. Are they? Yes! Its partial sums are bounded, and that's easy to show. Look, would you agree the partial sums are bounded by this is less than 1, this is less than 1, this term is less than a half. And would you agree with the next term, 1 over 3 factorial, is less than 1 over 2 squared? Because this is 1 over 2 times 3, and this is 1 over 2 times 2. Yes? This is smaller. Would you agree the next term is actually less than 1/8? Because this is 2 times 2 times 2, and this is 2 times 2, 3 times 4. Yes? So if you add up these things, these partial sums are bounded. In fact, they're bounded by what? If you sum up this, the most it can be is what? 3. This is the idea, right? Good. Partial sums are bounded. It's non-negative. And the terms are non-negative. Nice. So it converges to something. Let's call that number E. We'll call it E. We don't know anything about E. Well, I do. But let's call it E. Here's a question for you. How fast does this converge? I claim that this convergence is actually very rapid. The convergence is rapid. Why? Check this out. If I take E and I subtract off its nth partial sum, so the partial sum here is, I didn't write it out, but let's call the partial sum S. This would be S sub 2, and this would be S sub 3. Go out to the nth term. What do you get? Well, that's just 1 over the sum of the reciprocals from n plus 1, right? Okay. But check this out. Would you agree, whatever this is, I could factor this. I can factor out a 1 over n plus 1. This is just fun. It's not really like, there's nothing deep happening. I'm just showing you something cool. Look, 1 over n plus 1. Look, this thing now is 1 over n factorial, yes? Plus, sorry, no. In fact, I'm going to pull out a whole 1 over n plus 1 factorial. Sorry. Then this is 1 plus 1 over n plus 1. 2, but if I make this less than or equal to, it's less than of 1 over n plus 1. Yes? And the next term is less than 1 over n plus 1 squared, because there's n plus 2, n plus times n plus 3. But I've just increased the denominator. Decreased the denominator, made this bigger, yes? So what I'm doing here is a comparison. Again, I've just kind of informally said this is less than, and really I'm just doing this by comparison. Okay, but what's this? It's a geometric series, right? And in fact, it converges to n plus 1 over n. So when all is said and done, what you see is how rapid is this convergence? The nth term is no farther from E, whatever E is, than this very, very small number. Okay? Okay, now why did I point that out? This is just fun. The reason I'm pointing this out is because you can use this to see very quickly that E is irrational. The convergence is so rapid, there's no way E could have been a rational number. Why? If E did equal a rational, let's say m over some n, well then consider the nth partial sum. Oh, this is so cool. It's going to blow your mind. Look. The nth partial sum, if I look at E minus Sn for the nth partial sum, would you agree it's 1 over n factorial n? So if I multiply that by n factorial, this is less than 1 over n. Agreed? Yeah? Would you agree that this nth partial sum is also positive? E minus S over Sn is positive because it's just, this is all the leftover terms, right? So this is positive, right? But now, if m over n is rational, if E is rational, some m over n, all the denominators here, there's something over n times n factorial. This should be an integer, yes? The Sn terms all have denominators that are n factorial or smaller factors of n factorial. You multiply by n factorial, you also get a integer. So if e were rational, then there would be an integer between 0 and 1 over n, which is clearly not the case. No, there is no such integer. There's no integer. This is where you say with indignation, there's no integer between 0 and 1. 0 and 1 over n. End of argument. Nice. Very nice. Okay, that's just fun with series. All right. Have a great time. Stick around if you have questions about the homework. Some of you have already asked me about this, but with the upper and lower limit question, it may be helpful to appeal to a theorem in the book that talks about the uniqueness of the upper and lower limits as things that are subsequential limits, and anything bigger has a certain property, anything smaller has a certain property. Stick around if you have questions about that, or see the tutors later tonight, and we'll see you next week.